In today's video, we'll be walking through problem 2 of stable matching on the week 1 worksheet. The problem statement is as follows. Imagine all jobs have the same preference list. In other words, there is a global ranking of candidates and jobs' preferences are directly determined by that ranking. Part A asks us to prove that the first candidate in the ranking has to be paired with its first choice in any ranking. We'll proceed using proof by contradiction. So we'll assume that the first candidate C star is not paired with its first choice J star in some stable matching. This means that there exist job candidate pairings J C star and J star C such that J is not equal to J star and C is not equal to C star. Since J star is C star's first choice, we know that C star prefers J star to J. And since C star is J star's top choice, we know that J star prefers C star to C. Hence, J star C star form a rogue couple, and our matching is unstable. But remember that we assumed that our matching was stable. So by contradiction, we know that C star must be paired with J star in any stable matching. Part B asks us to prove that the second candidate must be paired with its first choice if that choice is different from the first candidate's first choice. Otherwise, candidate 2 must be paired with their second choice. The proof is similar to that of part A. So if the second candidate's first choice is different from the first candidate's first choice, then the second candidate must be paired with its first choice, since otherwise, the second candidate and its first choice would form a rogue couple. To see this, notice that the second candidate does not prefer any job more than its first choice. And the second candidate's first choice job does not prefer any candidate that hasn't been paired already more than the second candidate. If the second candidate's first choice is the same as the first candidate's first choice, then the second candidate must be paired with its second choice, since otherwise they would form a rogue couple. This is because the second candidate's top choice among all unpaired jobs is its second choice, and the second candidate's second choice job doesn't prefer any other unpaired candidate more than the second candidate. Part C asks us to assume that we've determined the pairs for the first k-1 candidates in the ranking. We're asked to determine who should the kth candidate be paired with. We say that the kth candidate must be paired with its highest ranked job that hasn't been paired yet. And we can show this using a similar argument to parts A and B. Part D asks us to prove that there is a unique stable pairing. To show this, we'll use induction. For our base case, we say that the first candidate has to be paired with its first choice, which we proved in part A. For our inductive hypothesis, we'll assume that the kth candidate has to be paired with its top unpaired job. Now for our inductive step. If the k plus 1th candidate is not paired with its top unpaired job, j sub k plus 1, we know that j sub k plus 1 plus c sub k plus 1 form a rogue couple. And to see this, note that we have pairings j star c sub k plus 1 and j sub k plus 1c. We know c sub k plus 1 prefers j k plus 1 to j star, since j k plus 1 is c k plus 1's top unpaired job, and j star is also unpaired. j k plus 1 prefers c k plus 1 to c, since c k plus 1 is the highest ranked candidate that hasn't been paired, and c is also unpaired. Hence, ck plus 1 must be paired with jk plus 1. So by induction, there's a unique stable pairing, since there is only one possible pairing for each candidate that would not result in a rogue couple.